Hello, everyone. My name is Dr. Destenie Low, and I am an assistant professor at Carnegie Mellon University in Engineering and Public Policy and Civil and Environmental Engineering. Today, I am going to present to you a framework for understanding the equity and sustainability trade-offs of national decarbonization strategies. This is going to be focused on low carbon energy transitions, and I would be remiss if I did not acknowledge my PhD student, Tegan Goforth, who has been helping lead this analysis. The US is in major change with its energy system, technology deployment, and investment. Here is a map of the different power plants in the United States, where orange represents natural gas, gray represents coal, and pink represents nuclear. And so over the next 30 years, this profile is going to see drastic changes. There's been a lot of debates about renewable energy 100% by 2035, renewable energy 100% by 2050, low carbon by 25, low carbon by 2050. Should we focus on the US NDCs for the Paris Climate Agreement, or should we look at that 1.5 degree C pathway? And there's all of the different scenarios in between. And the question that we have is, which of these is going to be the most sustainable? So that's what we're hoping to help everyone figure out. So for the perceptions and for all getting on the same page about what does sustainability actually mean? So here I want you to think about what one or two words do you think of when you hear sustainable energy transitions? Okay, so hold that word with you, or those two words with you as we move on. So then if you took that word, then I would ask you to think about which technology is the most sustainable. So here we have a solar panel, we have wind farms, we have hydropower, as well as natural gas. So typically when I ask this in person, I typically hear people say either wind or solar. And that is not uncommon. Most people tend to have an environmental view, and wind and solar are very well known for having little or no operating emissions associated with their generation. But we know that the energy system is never going to be just one technology. So it's really about the system of technologies. So let's assume that we had a system that's 50% natural gas, 50% solar, or another system that's 50% natural gas, 50% wind. And so the question is now, which combination of technologies is going to be the most sustainable? And this one is typically a lot harder for people to think through, because the truth is that it depends, because every technology is going to have sustainability concerns. Right, with hydropower, we may be concerned with droughts and water use. With solar power, there's discussions about the sustainability, the variability, the unequal adoption rates. And then for natural gas and coal, there's a lot of concerns about air pollution emissions. And so we need a way to value these trade-offs and find the pros and cons for the different technologies in terms of their sustainabilities, but also recognize that as we are adding these technologies into a system, a sustainability of a single technology is not necessarily going to be equal to the sustainability of the system of those technologies, because the way that those technologies interact with each other will impact the emissions from ramping, or the amount of that technology that we need in order to displace the technologies that we would like to retire. So coming back to where we started with those one or two words, when I think of sustainability energy transitions, typically my word is trade-offs, because there's always going to be people that win and lose, and thinking about how those benefits and costs are distributed across populations is something we really need to include in our sustainability analyses. So at the top of that triangle, I have equality. This is typically what people may think of when they hear social sustainability. Then we also have development and transition, which is where I would place like the economic side of sustainability. And then we also have environmental sustainability. The motivation behind this work is that there are going to be health impacts that emissions have on different communities, and we need a forward-looking analysis that can identify potential pitfalls and who's going to win and lose in different sustainability transitions. The primary goal here is to understand how historical and current inequalities in the power system could persist even under decarbonization, especially as we are considering these different national level policies. When we are trying to ask ourselves how decarbonization policies might impact sustainability and equity across the US, we are considering it under these three branches. So cost, distributional equity, and environmental sustainability. Between cost and environmental sustainability, we might ask ourselves, how does minimizing system cost impact environmental and health outcomes? If we're thinking about environmental sustainability and distributional equity, we may ask ourselves, how is air pollution reduced across regions? And how does the distribution of different air pollutants change across those regions? And then between cost and distributional equity, we may ask the question of, how is low carbon investment tied to different income areas? Which areas are receiving the most investment? Is it in those marginalized communities, or is it in areas that have historically been receiving the most investment from energy technologies? Currently, the way that we look at energy system modeling is primarily through least cost optimization models, which are very economic driven. So if you are having a model and you want to figure out where it's going to go in the future, you would input a bunch of constraints and say, okay, choose the least cost technologies in order to satisfy all of my constraints. But a challenge here is that this may inadvertently harm the most vulnerable communities and exacerbate social inequalities, because we know that's how the power system's been planned this whole time, right? Minimizing cost. And minimizing cost does not guarantee an achievement of social equity. This flowchart is presenting our analysis framework. First, we input different decarbonization scenarios, which I'll explain to you on the next slide. We then feed these into an electricity system planning model. We are currently working with the National Renewable Energy Laboratory and using their READS model in this analysis. That model outputs the different generation by power plants, the system cost, transmission, and power plant investment. Taking this information, we then feed this into a cost analysis, an environmental sustainability analysis, and a distributional equality analysis. We then feed this into a trade-off and multi-criteria decision analysis, where we will be highlighting where we are winning and losing across the different objectives that we have for energy transitions. Here is the different decarbonization scenarios that we are considering in our analysis. Scenario A represents the base case, where all policies and standards are included. B and C represent our carbon caps. So these are going to be including the US nationally determined contributions, as well as that 1.5 degree C pathway carbon cap. Scenarios D through F represent the technology specific renewable energy portfolios, where we're going to have different timelines for deploying that renewable energy technology. And then G and H represent the low carbon technology requirements. These graphs show an example output of our generation from the NREL's READS model. The black represents coal generation, brown represents natural gas, red represents nuclear, the dark blue is going to represent hydropower, the green line represents biopower, the lighter blue represents onshore and offshore wind, yellow represents solar, and then the dark green at the top represents storage. So one of the big things that we notice is that in the base case, most of the energy generation is coming from coal, natural gas, and nuclear. So that's currently what we are doing right now. And by 2050, we see that wind and solar are taking over. Now, the biggest difference between scenarios A, E, and G are that wind will take over sooner in these other mandates. So in scenario E, the 100% renewable energy, we see that primarily the two technologies we're using to satisfy our electricity addiction, that electricity demand, is onshore wind and solar PV, with a sprinkling of CSP, storage, and hydropower, where CSP stands for concentrated solar power. Then in scenario G, the low carbon case, while we see that wind and solar are still the main energy technologies we're using to satisfy our demand, we are meeting a portion of that demand with nuclear and natural gas with CCS. Here, I'm going to talk about the emissions calculation that we are using to inform our air pollution analysis, where E represents the emissions, RI represents the emissions rate for technology I, and GI represents the total generation for technology I in year T. And this is summed over the total number of technologies. So this is going to be the emissions within a region. So first region up is that national level emissions. Here I am presenting you the national operating emissions for CO2 and particulate matter, or PM. The black line represents the base case. The blue dotted line with squares represents the 100% renewable energy by 2035 case. And the red circles represent the low carbon by 2035 case. So one thing that we see here is that the base case and the renewable energy 100% by 2035 case bound the emissions, but in general, we see a decreasing trend for these national operating emissions, which is great for decarbonization. And we see that our co-pollutant PM typically follows that trend of decreasing. When we include all of the other scenarios for calculating those emissions, we see that each scenario falls in between that base case and that 100% renewable energy by 2035 case. We also consider the life cycle emissions. And so I'm going to take a step back and explain that we look at operating emissions to account for those local impacts, because we know that particulate matter is going to affect people at the local level. But we also want to take into account national life cycle emissions that are, created over the lifetime of power plants, because we know that CO2 is a global pollutant, meaning that no matter where that emission is generated, it is going to be impacting the global population. So here, the biggest difference that we see between the life cycle and the operating emission is that PM actually is increasing for a portion of our modeling horizon, where between 2010 and 2025, the PM emissions are actually increasing. Now that has to do with a combination of deploying solar, PV, concentrated solar power, and biopower, as well as having those coal and natural gas plants online at the same time. But we also see that A and E will continue to bound our scenarios and the total amount of emissions that we may see across regions. These maps present the distribution of those emissions across regions in the United States. The READS model has a sub-national regional analysis capability of 134 regions. So we do want to note that prior to implementing this analysis, there should be a more detailed understanding of, where the power plants will be deployed, as well as a deeper subnational analysis, potentially at the census tract level. So here, focusing on the life cycle CO2 emissions in 2050, we see that the base case typically has the highest amount of emissions, and it's looking pretty good in scenarios E and G. So where we see that in scenario E, that 100% renewable energy by 2035, 88% of the regions are below that lowest level, below 2.5 tons of CO2 emissions per capita. And then in scenario G, we see that 83% have life cycle emissions below that lowest tier. And then in the base case, only 45% had reached that lowest level. The Midwest really stands out here, indicating that rural areas may be worse off than in the cities on a per capita basis. With the operating emissions, we see a much different picture here, even when still looking at the per capita emissions, where the base case, it seems like it's not concentrated in just one area. We see a lot in Texas, Florida, the coast, as well as the Midwest. The 100% renewable energy by 2035 is the best, where all regions across the United States are below 50 kilograms of CO2 equivalent per capita. And then in the low carbon case, we see that the Southeast may be the worst off here. And this is highlighted in the percent of regions that reach that lowest level, where in the base case, only 24% of the regions reach that lowest level of emissions. But in the low carbon case, we see 75%. And then in the best case, the 100% renewable energy case, we see 100% of regions reach that lowest level. Here we're highlighting the PM emissions in 2050 to understand how one of the co-pollutants will be affected by different decarbonization policies under our least cost analysis. And here we find that the base case sees the lowest level of life cycle emissions reaching that lowest case. But the low carbon case is actually not too far ahead. It's only 5% more of a regions are reaching that lowest tier of 2.5 kilograms of PM emissions per capita. And the 100% renewable energy by 2035 case has the best life cycle emissions, again, because it's seeing the lowest amount of fossil fuel deployment. We do want to keep in mind that health effects of PM emissions can include cardiovascular effects like heart attacks, respiratory effects like asthma and bronchitis. And so while decarbonization is great for climate change because it reduces global emissions, the other pollutants are also important to mitigate because of these local health effects. So zoning in on those local health effects, here we are presenting the operational PM emissions in 2050. And we see that the base case has the highest level of emissions as we would expect, with only 57% of regions reaching that lowest level of operation emissions per capita. Now, one thing that's surprising here is that the renewable energy 100% by 2035 case actually only has 84% of their regions reaching that lowest level. And that has to do with a lot of biopower deployment to reach that goal very quickly. And we see that that's going to impact potentially the Southwest regions as well as Maine. And then in the low carbon by 2035 case, we actually find that 96% of the regions in our analysis have reached the lowest tier, meaning that this could be the best from an operational PM emission standpoint. In our equity analysis, we consider numerous indicators for understanding how the distribution of air pollution may be fed across different regions. In the future, we will also consider the distribution of energy jobs, but that is not going to be included in this presentation. And some of the things that we consider are the emissions ratio, the Genie coefficient, median income, energy burden, and poverty level. Here, I'm going to provide a detailed description of the Genie coefficient, which is our measure of air pollution inequality across the United States. Here, if the Genie coefficient is equal to 1, that represents complete inequality, where 100% of the emissions accrue in a single region and everywhere else has none. And then a Genie coefficient of 0 represents complete equality, where all regions have the exact same amount of emissions. So the Genie coefficient for the distribution of air pollution is going to be a factor of the summation across regions, where within the summation, we are summing the regional population multiplied by each other times the observed air pollution values divided by the total US population and then multiplied by a summation across regional populations. as well as the observed air pollution value. So this is going to be a population-weighted Genie where we do take into account the number of people residing within each region. To highlight what we have done in our equity analysis, we're going to start by showing you some results from our median income analysis, where here on the map, we are showing you how that median income changes across the regions in our analysis. The lightest color represents those that make less than $50,000 a year, and the darkest color represents locations where the median income is above $70,000 per year. So here is a graph of the life cycle CO2 emissions across income group, where the black solid line represents the worst off group, those making less than $50,000 a year. And the red solid line is that upper bound of those making more than $70,000 a year in terms of median income by region. Here we see that, oh wait, I should also explain that the blue dotted line represents the emissions at $5,000. That was the lowest potential level on those maps that I showed you before. And here we see that in the base case, all emissions are above 5,000 kilograms per capita. And the difference between the highest and the lowest income group is about 20,000 kilograms per capita. Compared to the other scenarios, we see that E, that 100% renewable energy by 2035, and G, the low carbon by 2035, are both below 5 kilograms per capita, but the highest income group always has the lowest emissions across the entire time frame from a life cycle standpoint. And the lowest group continues to be the worst off throughout this entire modeling time frame. Now for the operating emissions, we see a similar trend where the lowest group continues to be the worst off, but the biggest difference here is that in scenarios E and G, which have their strict mandates for reaching the 100% renewable energy deployment or 100% low carbon technology deployment, once you reach the mandate, it is going to accrue to zero, but the lowest group or the most worse off group so the most worse off group, those that have less than $50,000 median income per year, are going to continue to be the worse off group, which is very important to consider as we are decarbonizing, because this could show that social inequalities may continue to persist under the current energy planning paradigm. Here we are showing you the life cycle PM emissions across income group. And we see, stark things that should be a little concerning, where the PM emissions in the lowest income group are increasing oftentimes, and the highest income group, that red solid line, is decreasing. So if we just look at the base case, for example, we see that the highest income group, that red solid line, actually has a decrease of 41% in their PM emissions, whereas from 2010 to 2050, the lowest income group sees increasing PM emissions from a life cycle standpoint by about 16%. Then in scenarios E and G, the highest income group is going to see the greatest decline in emissions with between 70 and 85% reductions, whereas the lowest income group, they start to see reductions, and then it either flattens out or it starts to increase again, leading to less benefits. So knowing ahead of time that low income groups may continue to be the worst off would allow policymakers time to consider how these different decarbonization policies may impact health effects like asthma and cardiovascular diseases. One of the big things to consider here is that biopower does have a big impact on those life cycle emissions because of the 100% renewable energy mandate, deploying a lot of biopower in the Southwest region. We also consider the operating emissions from a PM standpoint. And we see that once we reach those technology mandates, all groups reach zero for the operational PM emissions. But until we actually reach that mandate in that cutoff year, lowest income groups are always the worst off across the entire modeling year. And that is something that is concerning, because if those mandates change, that means that those marginalized groups may never fully reach that lowest level of air pollution emissions and may continue to see more health effects in their communities. We also have, widened that mandate. So before I showed you the 100% renewable energy by 2035 and the low carbon by 2035 case. And here I'm presenting you scenario F, which is the 100% renewable energy by 2050, and scenario H, which is the low carbon by 2050. And once again, we see that extending out those mandates beyond 2035, at least in our analysis, does show that the low income groups will continue to be the worst off until those mandates are strictly enforced. And that is something that is very concerning as we are thinking about energy transition and policies. And so that means that, we could actually continue to harm vulnerable communities as we are moving forward with energy transitions if we do not have strict mandates to decarbonize the co-pollutants in those communities. So in summary, what we have focused on here is the environmental sustainability and the distributional equality analysis, where in the environmental sustainability side, we've seen that while national emissions are decreasing, especially from a life cycle standpoint, this may not always be the case from the operational emissions standpoint. And, we need to consider how decarbonization goals will impact the equity and equality in sustainable energy transitions. We also have seen that rural areas may be worse off than cities by 2050 from a per capita standpoint. In terms of looking at the distributional equity and equality analysis, we have seen that low-income communities are worse off in terms of local PM emissions, and high-income communities tend to see greater reductions in those emissions and for those trends to persist across our entire modeling horizon. The CO2 emissions decrease across all regions, but again, low-income groups still have the highest emissions in all of our scenarios, and that is something that we need to consider as we are designing our decarbonization strategies and policies. A big highlight here is that having a framework that decides how to reach different decarbonization goals using a least cost paradigm does not guarantee equity in decarbonization and may not protect currently marginalized and vulnerable groups from continuing to experience high levels of these local pollutants, the co-pollutants, and the CO2 emissions in their regions. Future work is going to be focused on those trade-offs. That's my favorite word when I think of sustainable energy transitions. And here we really focused on that distributional equity and equality side of things, as well as the environmental sustainability from the emission standpoint. We need to integrate system costs, understanding how those costs change across regions. We're also going to include jobs in our distributional equity and equality analysis. And then in the environmental sustainability side, we hope to be able to include land use and water use in that analysis, because we know that moving forward in terms of climate change, droughts are going to be a big concern for the country. So in conclusion, we have presented a framework for tying a national decarbonization model with a sustainability and equality analysis. Oftentimes, we may be trading global emissions for local emissions, and we need to consider how the co-pollutants are going to impact those marginalized communities as we are trying to decarbonize. And so here, if you leave with nothing else, it should be noted that considering the trade-offs in an analysis between environmental sustainability and equality is key for understanding where we may win and lose under different decarbonization policies. This work has been supported by the NSF grant and the Wilson E. Scott Institute for Energy Innovation at Carnegie Mellon. Again, my name is Destenie Low, and my PhD student is Tegan Goforth. We thank you for having us and listening to us. And here are the other PhD students in our research team who we would like to acknowledge for helping support and give feedback in our work. So thank you very much, and I hope that you all have a wonderful conference.